Rightio, so we're looking at how we model data and trying to get, so what you've done is you've created, you've done an experiment, you've got some data, it'll be doing different things, hopefully there's some change between your independent and your dependent variable. Okay, so the first thing when you're doing this graphs is ask yourself, what's my independent variable and what's my dependent variable? The independent variable is the one that we are changing, the dependent variable is the one that we are measuring to see what impact it makes. So I'm not going to give you data. What I'm going to do first of all is look at the equations. So I'm going to look at the theory. Okay, so what we're expecting to see. I'm giving us two examples that aren't like the ones that you've got, but they're similar skills. Okay. So the two equations we're looking at are B equals mu Ni. Okay, and that's saying the magnetic field in a solenoid is equal to the permittivity of the solenoid times the number of turns times the current. Now let's hypothetically say I did an experiment between the number of amps, so the amps in the circuit, and the magnetic field. So what occurs in that experiment is that everything else is kept the same. So I'm going to define everything that's kept the same, which is mu and n. I'm just going to give that the term K. Okay, I don't really care about those things. I just want to know what impact. I want to know the impact that current has on magnetic field strength. So as you can see with that data, I've got B equals Ki. Now B, that was the one I was measuring, so this is where my magnetic field goes, and this is where my current goes. Now what I would expect to see in that relationship, so when I rearrange that equation, I can see that the relationship between magnetic field and current is linear, because the I has got nothing operating on it. It is just B equals Ki. So the equation B equals Ki should provide a linear equation. Now how did I get the expected equation? I rearranged it so that my dependent variable, my B, was by itself on one side of the equation. So if that was my data there, and I generated a trend line, like so, I can see that that supports my theory. Because I've got a linear trend for data that should be linear. The equation says it should be linear, my trend line says it's linear, all good. I've got an agreement. What if my data, instead of doing that, looks like this? I can see that as my current goes up, my magnetic field goes up. However, the trend line I get suggests a polynomial or an exponential relationship. Now what that tells me, and you guys probably can't see, or you can, it's pretty poor. What that tells me is that in some ways my data supports, because it shows that there is an increase in magnetic field as current increases, but the relationship doesn't support it. So because it doesn't give me the value B equals Ki, this equation actually says, it doesn't say B equals Ki, it says B equals Ki squared. That doesn't support my equation. So I would say that in some ways it supports my theory, but in other ways it does not. And I'd talk about the reason why that occurred. Now the reason that occurred could be down to errors, it could be down to some resistance in the wire, it could be down to all sorts of things. That's one example. Another example that I'm going to go through, let's just say I did an experiment where I had different planets. Alright? So I was dropping an object on a different planet and I wanted to know the impact, so I was recording, was changing the, I was changing the final velocity, let's just go with that, and I was recording the acceleration. It's a flawed experiment, but that's okay. As we know from kinematics last term, the relationship I expect to see is Vf squared equals Vi squared, and I'll bring you guys over too. Vf squared equals Vi squared plus 2AD. What I want to do is I want to rearrange that equation to get A by itself. So before I've done anything else, I want to get this variable by itself. I want to get A by itself because it is my dependent variable. So when I rearrange A, I get the equation Vf squared minus Vi squared divided by 2AD equals A. Now in this situation, I'm setting my Vi as 0, so my initial velocity is 0. I don't want to divide by A, sorry, 2D. I'm keeping my distance constant, Therefore, because my distance is constant, I can represent that with the variable k. So I'll just be clear because I made a little bit of a boo-boo there. Acceleration equals vf squared minus vi squared over 2d. Because my distance is constant, 2 is constant, I'm just going to let 1 over 2d equal k. My vi squared equals 0. So I can represent the equation as a equals some constant k times vf squared. So let's come back to our graph and see what we should expect. So what I'd expect with this graph here, and I'll swing you guys around as well, what I expect with this graph here is that as my VF increases, my acceleration should increase by a square level. So that's where I want to see that type of trend. I'd want to see A equals some value K times VF squared. That supports my theory because it links to the equation I'm expecting. If I got data that looked like this, that would not support my theory because that shows a linear trend which says that A equals KVF. Where K is equal to M, X is equal to VF, and Y is equal to A, if you want to go Y equals MX plus C. So that does not support my theory. It does suggest that as acceleration increases, as velocity increases final, so does acceleration, but it does not support my theory in the way that it's not showing a polynomial. It's showing a linear trend. Now there could be reasons for that. I could have error in my calculation. I could have been using a stopwatch. There could have been error in the recording of the velocity final. Maybe air resistance plays a role. Does that make sense? So what you're trying to do is look at your trend line. So the first thing you do is get your trend line. Once you have your trend line, the only advice I'd give you is try to avoid using polynomials too much, because very rarely do polynomials actually represent real world scenarios. If they do, it'll only be of order 2. So try and avoid using polynomials as number 1. The second thing I do is get my relationship, have a look at a few different ones. You could have powers to show inverses, you could have square roots, you could have linears, you could have, I think they're the main ones that we've come across, potentially exponential, but you won't come across that for a while. So linear, power, polynomial, they're the 3 big ones, potentially a square root. If you come across those relationships, you then look at your equation, you rearrange it to get your dependent variable. So in your equation, in your instance, the dependent variable is your acceleration. So before you start talking about theory and all sorts of stuff, you should be looking at acceleration and how should mass impact acceleration according to theory. Then look at your data and say, does that support that? Hope that helps.